All right, 7.2. You guys said you were pretty comfortable with 7.1. Most people, in fact, are mostly done with their homework, so let's talk about 7.2. Okay? 7.2 is hypothesis testing for the mean when we know the standard deviation. So guess what 7.3 is? Hypothesis testing for the mean when we don't know the standard deviation, right? That was kind of the way we did chapter 6 as well, right? Okay, so chapter 7, hypothesis testing for the mean when we know the standard deviation. In chapter 5, we learned that the sample size is if the sample size is at least 30, then the sample distribution for the sample mean is normal. Remember that? Okay. Last section, we learned that a way to reach a conclusion in a hypothesis test is to use a p-value for the sample statistics, such as the sample mean. Okay? Recall that when you assume the null hypothesis is true, a p-value of a hypothesis test is the probability of obtaining a sample statistic with a value as extreme or more extreme than the one determined from the sample data. Now, when I read that last period, it was like this. Blah, 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 blah. Okay? So I'm going to go back over that one sentence and make sure that we're all together on this. You okay with that? Okay. Recall that when you assume the null hypothesis is true, a p-value of a hypothesis test is the probability of obtaining a sample statistic with a value as extreme or more extreme than the one determined from the sample data. Is that any better? Little bit? Okay, good. The decision rule for a hypothesis test based on the p-value is shown below. So we like our red boxes. We see a red box. That's good. Okay. Decision rule based on a p-value. To use a p-value to make a decision in a hypothesis test, compare the p-value with that. Do you remember what that is? What is this right there? Do you remember that? You can't see it, I know, I'm sorry. It's that symbol that's right there. Let me show you real quick so that you remember. It does look like an A, and that's good, okay? I guess I didn't have that one marked. It is a lowercase alpha. Okay, it is a lowercase alpha. So we're going to compare the p-value with our lowercase alpha. So if our p-value is greater than or equal to alpha, then reject the null hypothesis. I know I marked that one. Okay, H sub 0 is the null hypothesis. H sub A is the alternative hypothesis. Do you remember that from section 7.1? Okay, so if our p-value is less than or equal to A, then reject it, the null hypothesis. If our p-value is greater than alpha, then fail to reject. Now, this is something that confused me for a while, so I want to make sure if it's confusing you that we can at least talk about it. Why do they use that language? Doesn't a double negative mean that we accept it? Well, not necessarily. Okay? It seems weird we would use a double negative, fail to reject, right? But just because we failed to reject it doesn't mean we're accepting it. It means there's not enough information. Does that make sense? So we can either reject it or not reject it. But by not rejecting it, we are not accepting it necessarily. We're just saying we're not rejecting it. Does that help? It could be true, but we don't have enough information to know that for sure. You okay with that? Okay, but that's the language, that's the vocabulary that we're going to use. We're either going to reject it or we're going to fail to reject it. Okay? Okay, example 1. We've got 10 examples in this section to get through. One of them I'm not going to do, and another one we're probably just going to talk through. You'll see when we get there, okay? Example 1. So interpreting a p-value. If a p-value for a hypothesis test is 0.0237, what's your decision when the level of significance is 0.05? Well, how does 0.0237 relate to 0.05? It is less than, and because it's less than, we reject. Does that make sense? Okay. What about if alpha is 0.01? 0.0237 is greater than 0.01, so we fail to reject the null hypothesis. You okay with that? Okay, look at the try it yourself right below that. Okay, it says the p-value for our hypothesis test is 0.0745. What's your decision when alpha is 0.05? Why are we going to fail to reject? 0.0745 is greater than 0.05. Yes, so we fail to reject, right? Because p is greater. Okay, what about when alpha is 0.1? 0.05 is less than 0.1, so p is less than alpha, so we reject it, the null hypothesis. You okay with that? Okay, so right below that gives us another red box. Yes, we love our red boxes. Okay. After determining the hypothesis test, oh, Jiminy Christmas. After determining the hypothesis test's standardized test statistic, say that 5 times fast, although I really don't want you to, okay? And the standardized test statistics corresponding area, we want to do one of the following with the p-value, okay? If it's a left-tailed test, p equals the area in the left tail. If it's a right-tailed test, p equals the area in the right tail. If it's a two-tailed test, p equals 2 times the area in one of the tails. The area in the tail of the standardized test statistic. Does that make sense? Now, I was kind of excited when I read this because I already know how to do this. I know how to find the area in a tail, right? So now I'm just having to put some things together that I already know how to do. All right? So let's go to the next page. Example number 2. Find the p-value for a two-tailed hypothesis test with a standardized test statistic of z equals negative 2.23. Let's get our charts out. That's exactly what we need to do. Okay, we need to get our z tables out. Here's 1/2 of my z table. Fortunately, it's the one I need, right? Z equals negative 2.23. So negative 2.23. 0.0129. Okay? 0.0129 is, sorry, that's the area, right? So that's my p-value. My p-value is 0.0129, which is the area in the left tail. So how does that compare with an alpha of 0.01? Well, because the p-value of 0.0129 is greater than that of 0.01, we fail to reject. Okay? Got it? Okay. What about a two-tail? Because that was just a left tail, right? So let's look at a two-tail real quick. I think I said two-tail, but I meant left tail. I'm sorry. Okay. So find the p-value for a two-tailed hypothesis test when z is 2.14. Well, that means I have to find my other page of my z table, which is right here. What is it? 2.14? So 2.14, 0.9838. So p is, let's see, why are we having to subtract it from 1? Do you guys know? Do you remember that? The area corresponding to z is 2.14, which is 0.9838. So that's this area, right? That's that area in the middle, not the tails. So I have to say 1 minus that to get 0.0162. Do you see that? Well, because it's a two-tailed test, I have to say 2 times 0.0162. Does that make sense? So that gives me 0.0324. Well, let's decide whether to reject the null hypothesis if the level of significance is 5%. or 0.05. How does 0.05 compare to 0.0324? Okay, so what are we going to do? Reject. You okay with that? Because remember our rule right here, if it's greater than, if the p-value is less than, then we reject the null hypothesis. Okay? And our p-value was the 0.034, and that is less than 0.05. Okay? Okay so far? Okay, so let's use p-values for a z-test. Using p-values for a z-test. So this formula for z, is that something we already know? Is that a formula that you're familiar with? It is, isn't it? The sample mean minus the hypothesized mean divided by the standard error. Top of page 365 is the formula I'm looking at. Okay? Are you good with that? So the z-test for a mean is a statistical test for a population mean. The test statistic is the sample mean. The standardized test statistic is z, and it gives us the formula for z right there. Standardized test statistic, okay, when the standard deviation is known. All right? So first of all, that z formula only works when two conditions are met. Number one, the sample has to be random. Okay? Number two, one of the things has to be true. Either the population has to be distributed normally, or our sample size has to be greater than or equal to 30. Now the good news about that is we've already had to do things with those two things were true, right? It had to be normal, and either it had to be normally distributed, it had to be random, or it either had to be normally distributed, or it had to be a sample size greater than 30. That's something we've already had to deal with, right? So we're not having to learn new numbers or new boundaries or anything like that. We have that already, okay? Now, it also says recall that standard deviation divided by the square root of the number of terms in our sample is the standard error of the mean. So we've already done even that. Okay, it already showed that to you in the formula right up there. So again, that's something we're familiar with, right? Okay, then right underneath that is a yellow box. I also like the yellow boxes. I'm not sure about you guys, but I like the yellow boxes because it gives me guidelines. It gives me like steps to follow when I'm doing a certain problem. Okay, so first of all, it says verify that the standard deviation is known, verify that the sample is random, and either it's distributed normally or my n is greater than 30. Okay, again, that's something common we've had to do already, right? Okay, then state the claim. Figure out h sub 0, which is our null hypothesis, and figure out h sub a, which is our alternative hypothesis. Okay. Specify the level of significance. Now, in any of the examples that it's shown or any of the problems I've seen, we don't ever have to choose what our alpha is. It'll say our alpha is 5% or our alpha is 0.05. It tells us that. We're not having to decide that. You see what I'm saying? Okay. Then find the standardized test statistic. So use the z formula. Find the area that corresponds to that z value. So use your z tables. And then find the p-value, because that's going to be the area that's underneath the tails. If it's left-tailed, p equals that area. If it's right-tailed, p equals that area in that tail. And then if it's two-tailed, then it's 2 times that area. Got it? Okay. Make a decision. So if the p-value is less than or equal to the alpha, then reject the null hypothesis. If the p is greater than that alpha, then fail to reject the null hypothesis. Okay? And then interpret the decision based on the context of the original claim. Nice little guidelines to have, right? Okay. Example 4. Let's do an example about what we just talked about. Using a p-value. Okay. In auto racing, a pit stop is where a racing vehicle stops for new tires, fuel, repairs, and other mechanical adjustments. The efficiency of a pit crew that makes these adjustments can affect the outcome of a race. Okay, so a sidebar comment real quick. Have you guys ever watched auto racing? Have you ever watched how fast a human man or human woman can take a tire off and put a tire back on. Like, it is amazingly fast. I don't know how they do it. I think it's a talent. That's just my own opinion. Okay? This particular pit crew claims that it can make these adjustments, that its mean pit stop time is less than 13 seconds. Now, somebody in last period said that they like to watch NASCAR and 13 seconds is like, okay. So maybe that's like the JV time. But still, it's pretty darn good, right? Because I definitely can't change a tire in 13 seconds. More like 13 hours, okay? Maybe minutes, probably double that or something, okay? Anyways, a random sample of 32 pit stop times has a sample mean of 12.9 seconds. Assume the population standard deviation is 0.19 seconds. Is there enough evidence to support the claim at that alpha being 0.01? Do you remember what the alpha stands for? Remember what the words are that correspond with it? Level of significance. Does that help? That's the 5% or 1% or whatever. Okay, just helping you remember what the symbols stand for. And quite honestly, helping myself remember what the symbols stand for. Okay? All right, so first of all, do we know the standard deviation? Yes, it tells us, right? Okay, do we know the sample's random? Yes, it tells us. Okay, do we know that it's either normally distributed or that the sample size is greater than 30? It's greater than 30. It's 32, in fact, right? Okay, so that's good. So since we know those two things, then we can use the z-test. So we use all these numbers that were given to us before. Oh, in just a second, sorry. First, we have to talk about the null hypothesis and the alternative hypothesis, right? So we're saying that the null hypothesis is that it's greater than 13 seconds, and the alternative hypothesis is less than 13 seconds. That's the claim, right? Less than 13 seconds. Okay? So the level of significance is 0.01. So now we can use our z-test. Plug in all our numbers that we know that were given to us in the problem, and we find out z is approximately negative 2.98. Why is it approximately negative 2.98? Well, we rounded, first of all, right, in our calculations, because we don't know the exact square root of 32, do we? Okay, so we rounded. Plus, why did we round to 2 decimal places? Anybody remember? How many decimal places does our z-table go to? 2. Okay, so we know our z-table goes to 2 decimal places, so we want to make sure that this number is rounded to 2 decimal places. Okay, so let's find the corresponding area on our z-table to negative 2.98. Let me get my z-table back out. The right one. Goodness. Negative 2.98. Right there. 0.0014. Oh, look, 0.0014. It's right. Okay? Because it's a left-tailed test. Now, it took me a second to figure that out. Okay? How do I know it's a left-tailed test? In the words right here, it says, because it's a left-tailed test. How do I know it's a left-tailed test? Look back up to your alternative hypothesis. If our alternative hypothesis is something is less than 13 seconds, that's going to be a left-tailed test. Does that make sense? If I look at my alternative hypothesis and it is greater than something, that's going to be a right-tailed test. What is our other possibility? Two-tailed test, right? So what does our alternative hypothesis have to be if it's a two-tailed test? Equal. Okay? So looking at all our alternative hypothesis is really going to help us know whether it's left tail, right tail, or two tail. Okay? Because we kind of have to know that, don't we? All right. So because the tail is left tail, because the test is left-tailed, the p-value equals to the area to the left of z equals negative 2.98. So p equals 0.004. How does 0.0014, how does that number relate to 0.01? Well, 0.0014 is less than 0.01. That alpha, the level of significance is greater than that, but we really concentrate on our p-value being first. Our p-value is less than our level of significance, and so we reject the null hypothesis. Does that make sense? Okay, so the interpretation is there is enough evidence at the 1% level of significance to support the claim that the mean pit stop is less than 13 seconds. Yes? Okay. Example 4 is, well, if I could read, it's example 5. Example 5 is the same kind of thing. It's talking about the cost of bariatric surgery. The only difference this time, besides the numbers obviously, is that our null hypothesis is the fact that it is 21,500, and that means the alternative hypothesis is that it's not 21,500. And since it's either equal or not equal, guess what kind of test it is? Two-tail, right? Okay, so there's a picture down here on the side, so you know that it's two-tailed. All right, you get your hypotheses. Yeah, we get those here. We find our z-value. We use our z-value to find the area. Because we know that it's two-tailed, we have to multiply that area by 2, which gives us this value, 0.0734. How is that related to 0.05? Well, it's greater than 0.05, that 5% level of significance. And so there's not enough evidence, so we will fail to reject. Okay? The failing to reject tells us that there's not enough evidence. All right. Example 6, that's the one I was telling you we're really not going to talk through because that's with technology. We've really already talked about that in previous chapters. We've got our z-tables pretty much set up and we know how to read those, and so we're just going to go on. Okay. On the bottom of page 368, it talks about rejection regions and critical values. Now, to me, when I read something called critical values, it seems like it's pretty important. Well, that's because it is. Okay, it's called a critical value. It's a really important value in a situation like this. Okay, it's another method to decide whether to reject the null hypothesis or fail to reject it, and that depends on whether it falls into a range of values called the rejection region. Now, personally, as a human being, I never want to be in the rejection region, just for the record. Okay, that kind of hurts your feelings. Yeah, you live there? Okay, I'm very sorry. I always accept you. You're never in my rejection region. Okay. A rejection region or a critical region of a sampling distribution is the range of values for which the null hypothesis is not probable. Does that mean it will never fall there? No, it's just saying it's not probable. Okay. Statistics is almost hardly ever about absolutes. You notice that I didn't even use an absolute in the description of it. That was funny. Okay. If a standardized test statistic falls into this region, then the null hypothesis is rejected. A critical value, z sub 0, separates that rejection region from the non-rejection region. Okay. Oh, good. There's some guidelines. We always like our guidelines, right? Okay. Specify the level of significance. Again, we're looking for it because it's going to tell us that. Okay. Now, there may be a situation where you have to figure that out, and if there is, we'll talk through that. Okay. Next, determine whether the test is left, right, or two-tailed. Then find the critical values. When the hypothesis test is left-tailed, we want to find the z-score that responds to the area of the alpha. Okay, so what we're saying now is we're going backwards, right? Before we found the z and used the z-table to find the area, now it's telling us the area. Guess what we're finding? The z. We're just going backwards. But that's something we're comfortable with because we've done it before, right? Okay, it's just meaning different things this time. We're talking about left-tailed and right-tailed tests and everything like that. Okay, if it's right-tailed, we're finding the z-score that corresponds to the area of 1 minus the level of significance. And then if it's two-tailed, we find the z-scores that correspond to half of the level of significance and 1 minus half of the level of significance. Why are we using half? Remember, we're talking about the area of two-tail. If we know that area, we know it's half here and half here. That makes sense? Okay. And then you want to sketch the standard normal distribution, draw a vertical line at each of the critical values, and then shade the rejection regions. Yeah? Left tail, right tail, two-tail. Okay? When you cannot find the exact area on table 4, what do? Look for the one that's closest, right? Look for the one that's closest. What if it's exactly halfway in between two of those values? Yeah, put the 5, right? We go halfway in between those two values, even on our area or our level of significance number. Okay? Example number 7, finding a critical value for a left-tailed test. Well, if we do left tail, don't we mostly know right tail? Just the 1 minus the number kind of thing? Okay, left tail. It says find the critical values in rejection region for a left tail test with a level of significance of 0.01. Well, what do we look for on the table? 0.01? Well, the closest thing to 0.01 looks to me like that one. Okay, it's 0.009. That's pretty close to 0.01, right? So that's going to be negative 2.33. Oh, look, negative 2.33. Yes. So the critical value is negative 2.33. So we drew the little standard normal curve, and we have our different standard deviations at the bottom. I know my z value is negative 2.33, so I've got a vertical line there. That's my critical value. Okay? Does that make sense how you would do a right tail also? Okay, because the next example that shows us is just for a two-tailed test. Okay, but it's the same kind of thing, guys. You're just following using the formulas that they gave us in the guidelines to the left of this. We have a level of significance of 0.05. If we look for 0.05 on the z-table, is that what we're going to look for on the z-table, is 0.05? Well, what happens if it's a two-tailed test? Is it really 0.05 under each one? Or is it 0.025 under each one? It's half of that, isn't it? So 0.025 is what we actually look for on our z-table. Okay? So looking for 0.025 on our z-table, we're going to find that at negative 1.96. Do I need to show you that? Negative 1.96 is right here, 0.025. It's exactly that, right? So I know that that half is over here, and then the positive 1.96 is the other half. I draw that, draw our critical values, go on. Okay? So here's the good news. We just did example 8. Good so far? There's a lot of information in this one chapter, isn't there? Or this one section. Please don't get overwhelmed. You're okay. Okay. Using rejection regions for a z-test. Red box. Yes, we love our red boxes. To use a rejection region to conduct a hypothesis test, calculate the standardized test statistic z. If the standard test statistic is in the rejection region, then reject the null hypothesis. If it's not in the rejection region, then fail to reject the null hypothesis. Okay? On the top of page 370 that you have there in front of you, it gives you 3 diagrams of that. If your z value is in that rejection region, then reject it. If your z value is not in that rejection region, then fail to reject it. Does that make sense? Okay. Remember, failing to reject the null hypothesis does not mean that you have accepted it. It just means that there's not enough evidence to reject it. We talked about that a minute ago, didn't we? Okay. Guidelines, yay! Okay, guidelines for rejection regions for a z-test when you know the standard deviation. Okay, so verify all that stuff is true that we talked about, that we know it's standard deviation, that the sample is random, that it's either distributed normally or that the sample size is greater than 30, right? Okay, then know your null hypothesis and your alternative hypothesis. Make sure you specify your level of significance. Determine your critical values using your z-values. Determine a rejection region. Use this formula to find your z-value if you need to, and then make a decision to reject or fail to reject the null hypothesis. And then last but not least, if you need to, interpret the decision based on the original claim. Okay? This is the last example I'm going to show you. Like I said, there is an example 10, but example 9 just talks about using the rejection regions. It talks about employees at a construction company has a mean salary of $68,000. Another company, they're saying, earns more than that, or less than that. Sorry, it's saying the random sample of 20 are saying that it's $66,900. So we're saying our null hypothesis, our alternative hypothesis, which is our claim, is that it's less than 68,000, which means our null hypothesis is that it's greater than or equal to 68,000. Okay? Use your use your z formula to find your z value. Use that to find your area. And you will figure out that there's not enough evidence at a 5% level of significance, which is what they ask you for in the problem, to support the claim that it is less than 68,000. Okay? Does that make sense? Read through this problem again if you want to. Ask me questions. We can talk about it later. Example 10, if you want to look through that, that's a two-tail situation. This one is a two-tail. The one we just talked about right here, example 9, is a one-tail. That's the only difference between those two examples. Got it? Got it. Awesome. Peace.